Upstairs above the corner cafe, Sarah had turned the quiet reading room into a tiny chemistry classroom.
Today we begin with one question. Can matter disappear?
If yesterday's muffins count as matter, then yes. They disappear very quickly.
Ben, that is not a scientific observation. That is breakfast.
Good distinction. Science starts with careful observation, then measurement, then evidence.
I am ready to observe, measure, and emotionally support the muffins if necessary.
I had calibrated the digital scale. Current confidence acceptable.
Excellent. Our key words today are mass, matter, and evidence.
Theo placed a sealed jar, a small cup of baking soda, and a little bottle of vinegar on the tray.
Before any reaction happens, we measure the reactants. That gives us our starting mass.
Digital scale reads 142.6 grams. Recording value now.
So the number is not decoration. It is the evidence we will compare later.
Exactly. In chemistry, a claim becomes stronger when a measurement can support it.
I respect any subject where the scale has to tell the truth before the drama begins.
I have labeled the situation reactants before rearrangement.
Good. Our question is not only what happens, but how we know.
Theo poured the vinegar into the open jar, and pale foam rose like a tiny cafe cloud.
This is a safe acid-base reaction. Watch carefully, but do not guess too quickly.
The foam looks like it is trying to escape the lesson.
If something leaves the jar, then our measurement might change for a reason.
Visible evidence. Bubbling. Possible invisible evidence. Gas leaving the open system.
Open system means the jar is allowing visitors to exit without signing out.
That is surprisingly accurate. In an open system, matter to move in or out.
We will measure again soon, but remember, a lower number would not automatically mean matter disappeared.
When the foam settled, Mabel 7 placed the tray back on the digital scale.
New mass reads 137.9 grams. Difference 4.7 grams.
That is less. The grams escaped, or got promoted.
Starting mass was 142.6 grams, so the change is real.
Careful. The number changed in an open setup, and the setup matters.
Good observation. Now we need a conclusion that explains the evidence.
Hypothesis the missing grams became atmosphere with confidence.
More formally, gas may have left the container.
Sera wrote 3 possible explanations on the board, and the room became very quiet for about 2 seconds.
Option 1. Matter vanished dramatically and refused to leave a forwarding address.
Option 2 the atoms departed politely to the top of the jar.
Option 3. Gas escaped, so the remaining system had less measurable mass.
The third idea matches the bubbles, the open jar, and the lower number.
Yes, but we should separate observation from inference before we celebrate.
Exactly. An observation is what we measure, and inference is what we think the evidence means.
So the scale gives us the plot twist, but not the whole explanation.
Sera drew a 3-step chain on the board: observation, inference, conclusion.
Our observation is lower mass. Our inference is that gas escaped. Our conclusion must be tested.
So a conclusion is not just a confident sentence. It has to survive evidence.
Exactly. If gas escaped because the jar was open, then closing the system should change the result.
Testable prediction. In a closed system, total mass should remain the same.
Science is basically making your idea walk through airport security.
I will prepare the concept luggage.
Good. Next, we compare an open system with a closed system.
Mabel 7 rolled a small diagram board beside the lab table.
Open system, matter can enter or leave. Closed system, matter cannot enter or leave.
Same reaction, different boundary.
Boundary means the science fence.
Better, a boundary is the limit of the system we are studying.
So if gas stays inside the boundary, the scale should count it.
The grams were not gone. They were outside our counting boundary.
Exactly. Conservation of mass depends on measuring the whole system.
Theo brought out a second tray, a sealed reaction jar, and a clear safety bag for the closed system test.
Before we react again, we slow down and make a prediction in complete academic English.
If no matter can leave the system, then the total measured mass should stay the same.
That is stronger than saying, I think it will be fine. It tells us what result to expect.
Prediction recorded. Closed system before reaction, 142.6 grams.
The gas will not escape. It will attend the entire lesson.
Imagine being a gas bubble and realizing the door is locked for science.
The joke is welcome, but the boundary is the important part.
We are not changing the reaction. We are changing what counts as the system.
System boundary includes the sealed jar, the liquid, the solid, the gas, and the tray.
So this scale is not just weighing the jar, it is weighing everything trapped inside the boundary.
Exactly. A careful experiment defines a system before interpreting the number.
Boundary definition complete. Gas attendance policy strict.
Everyone leaned closer because the second measurement would test the explanation, not just repeat the surprise. Theo started the same safe reaction inside the closed setup, and the foam rose behind the clear wall of the jar.
Same reactants, same reaction, but this time the gas remains inside the measured system.
The bubbles look offended, but they are staying in class.
I can still see evidence of gas forming, but now the gas is contained.
After reaction mass is 142.5 grams.
That tiny difference is within ordinary measurement uncertainty for our classroom scale.
So we do not overclaim. We say the mass stayed essentially the same.
The open system looked like mass disappeared because gas left the boundary.
The closed system kept the gas inside, so the scale counted it.
Conclusion: matter did not vanish. It merely changed seating arrangements.
More formally, atoms rearranged into products, but total mass was conserved.
I enjoy a universe where the grams are dramatic but still accountable.
That is conservation of mass. In a closed system, matter is not created or destroyed.
The missing grams were no longer missing. They had simply been outside the first measurement. Sera gave everyone one final challenge: turn the experiment into a clear scientific conclusion.
A strong conclusion does three jobs. It answers the question, uses evidence, and explains the reasoning.
Claim matter did not disappear during the reaction.
Evidence: in the closed system, the mass stayed essentially the same before and after the reaction.
Additional evidence: in the open system, the mass reading decreased because gas could leave the boundary.
So the open jar gave us the mystery, and the closed jar gave us the answer.
Mystery jar was dramatic. Answer jar was responsible.
Reasoning: gas is matter. If the gas leaves the measure system, the scale no longer counts it.
But if the gas stays inside a closed system, the total measured mass remains conserved.
So the better sentence is, mass is conserved when we measure the whole system.
Suggested wording: the apparent loss of mass was caused by gas leaving the open system, not by matter disappearing.
That sentence sounds like it has a tiny graduation cap.
Good. Academic English is not about sounding fancy. It is about being precise.
The class wrote the conclusion carefully because a good explanation should be warm, clear, and hard to misunderstand. Sera erased half the board and wrote one practice question in large, calm letters.
Practice question, a student says. The mass went down, so matter was destroyed. What is wrong with this conclusion?
It ignores the system boundary. If gas left an open container, the measured system changed.
Good. The student noticed a real measurement but interpreted it too quickly.
Correction: the mass of the remaining open setup decreased, not necessarily the total mass of all matter.
So the problem is not the scale. The problem is the sentence bossing evidence around.
Evidence does not enjoy being bossed.
Exactly. Strong academic writing respects the limits of the evidence.
A better answer would mention open system, gas leaving, and the need to measure the whole system.
And if the setup is closed, the gas stays inside, so the scale can count it.
Final practice answer: the apparent loss of mass can be explained by gas escaping from the measured system.
That answer is less dramatic but annoyingly correct.
In science, annoyingly correct is often excellent.
Everyone wrote the answer down because the best lesson is the one you can use again. The afternoon light warmed the classroom as Sera closed the lesson with one final board.
Today we learned that conservation of mass is not just a slogan. It depends on careful measurement.
Matter can change form, atoms can rearrange, and gases can be easy to miss.
But if we define the system carefully, the evidence becomes much clearer.
Key rule: in a closed system, total mass is conserved during a chemical reaction.
Secondary rule: never let gas leave without completing the attendance sheet.
I support that rule emotionally, though not legally.
The real rule is simpler: measure the whole system before making a conclusion.
Next time, we can use the same thinking to study reactants, products, and balanced equations.
So chemistry is not only formulas. It is careful language plus careful evidence.
Lesson status: missing grams located, concept stabilized, curiosity increased.
And no muffins were harmed except the ones from earlier.
Downstairs, the cafe bell rang, and the class carried one new idea with them. Matter may move, but it does not simply vanish.
That is conservation of mass.